So it's time now to solve some real examples. In this exercise we have the arm OA. If you look at this figure, we have the arm OA rotates from the left to the right with an angular speed of 0.5 radians per second. So when it rotates, it will pull on its way cylinder C. So the cylinder C has a mass of 2 kilograms. So it has a mass of 2 kilograms. And we have the angular speed of the arm OA is equal to 0.5 radians per second. And they ask me to determine the force that the arm OA exerts on the peg at theta is equal to 60 degrees. So the first thing here is that I notice is that we are looking for force. Since you are looking for force, you will need to set up the equations of motion. Okay. So to set up the equation of motion, you will need free body diagram. So in free body diagram, you have to be very careful because you are going to isolate the mass. You are going to isolate the mass, and once you isolate the mass from its environment, you will need to represent the environment in terms of forces. Okay, in terms of forces. So we start with the most important force, which is the weight. And we notice that the cylinder is actually supported first by the horizontal plane, so it is supported here. So once I remove the support, I have to represent the action of that support with the force N. Okay, this is the force that we call reaction force or normal force. I like to call it reaction force, which is always normal to the surface. Now, when the arm OA moves to the right, it pulls actually the cylinder to this direction. So when it pulls the cylinder to that direction, this side of the arm OA is actually supporting the mass. Okay, it's supporting the mass. So basically, it will have an action on the mass because it is supporting the mass. So there will be a force that is perpendicular to that side of the arm OA, and that force will act upon the mass. Okay, so if I put here just to represent here that side of the peg, that side of the arm OA. This is the other side of the arm. So once I remove the arm OA, I will have to represent its action on the mass with this force. Okay. Of course, it has to be perpendicular to this side. Good. Now that I have the free body diagram, it is time to choose what is the best coordinate system. Here it's very simple exercise. Since it is easy to notice that since you are given the angular speed, you will have to use the cylindrical coordinate system. Okay. So I'm going to assume that the origin is here, and the radial axis extends from here until here. Okay, and let me just write here in red. And the transverse axis, so that's the radial axis, is perpendicular to it, and it will pass through, of course, F, because F is perpendicular to the arm of OA. So this is the radial axis, and this is the transverse axis. Good. Now, of course, this will be the direction of the radial acceleration, and this is the direction of the transverse acceleration, a theta. Okay, good. Now, what I'm looking for is actually the normal reaction force of the arm OA on the cylinder. So I'm looking for the force F. So since the force F is on the theta axis, okay, transverse axis, naturally I have to start with the sum of the forces in the transverse direction. So before that, I write the general equation of motion. Sum of the force is equal to mass times acceleration, and here I assume using the cylindrical here we're using polar, okay, coordinate system. We'll have sum of the forces in the transverse direction equals the mass times the transverse acceleration. Okay, so which means what I have here, we have the force F, which is positive, minus this component of the weight, this component of the weight. Okay, sorry. So this component of the weight is simply mg, and I'm going to use so if this is angle theta, okay, so if this is angle theta, then this will be also theta. So since this is theta, so this also is theta. So it will be mg cosine theta. Okay, so minus mg cosine theta, negative because it's opposite sign. Okay, and we have here the another force, which is the normal reaction force of the horizontal support. So this support, we are talking about N. So it has a component on the transverse axis, and this is the one. So this component is simply N times, so if this is the angle theta, this would be also theta times cosine theta. Okay, so but it is positive because it is in the positive direction of the transverse axis. So plus and cosine theta, and this should be equal to m times a theta. Okay. Now what I'm looking for is actually F. So do I have theta? Yes, they give me theta is equal to 60 degrees. The mass I have at 2 kilograms. G, I have it 9.81 meter per second square. Now here is the issue. I don't have N, the reaction of the horizontal support, and I don't have also theta, A theta. I don't have the transverse acceleration. So this is the issue. I don't have N and I don't have A theta. Imagine if I have N and A theta, it will be easy to calculate the force F. So let's start one by one. So N, it has another component on the R axis, okay, on the radial axis, okay. So that component is this. Let me just put it in black. Okay, we are talking about this component, okay. Now this component is N sine theta, okay. Since N appears on the radial axis, naturally I'm going to set up the equation motion the R axis, okay. So we have sum of the forces in the radial direction is equal to the mass times the radial acceleration, which means I don't have a component of the force F on the radial axis, so we have 0. We have another component of the weight on the radial axis, and that component is positive, okay, and this component is simply W sine theta, okay. So what we have here, we have W sine or mg sine theta, it is positive here, minus n sine theta. This will be equal to m times the radial acceleration, okay. Now the issue here is that now I'm looking for n, but I don't have the radial acceleration. I have two equations, equation 1 and equation 2, but the problem is that I have unknowns, and in addition to F, I have unknown N and another two unknowns. So I don't have AR, I don't have A theta. Assume that I have AR. I will be able to calculate N using equation 2. Then, assuming that I have A theta, I will be able to calculate F. So now my issue is to calculate AR and A theta. Now we know from kinematics that AR is equal to R double dot minus R theta dot square, and A theta, the transversal acceleration is equal to R theta double dot plus 2R dot theta dot, okay. Now R, they give it to me, they haven't given it to me, okay. We don't know R. Imagine I have R as a function of theta, okay, or as a function of time. I will be able to calculate R dot and R double dot, okay. Theta dot is given to me. It is equal to 0.5 radians per second. It is constant, so this guy will go to 0. The second derivative or the angular acceleration goes to 0. So we have theta dot is equal to 0.5 radians per second. Now how do I calculate the R as a function of theta? If you notice, we have the height or the vertical distance between O and C is equal to 0.4 meters. So if you look at the triangle, we have here 0.4 meters. This is R and this will be theta. So we are looking at this triangle. Okay, we are looking at this triangle, okay. So this is R, this is 0.4, and this is theta. Okay. Now if you calculate sine of the angle theta is equal to 0.4 divided by R. So R is equal to 0.4 divided by sine theta. Okay. Now I don't recommend differentiating R starting from this equation. Okay, it's always easier to differentiate the following. We have R sine theta is equal to 0.4, right? Now, if we differentiate with respect to time, this equation R sine theta is equal to d over dt of 0.4, what we get? R sine theta, it is the product of two functions. Okay, we are differentiating with respect to time, so we will have R dot sine theta. Recall that f g prime is equal to f prime g plus g prime f. Okay, so we have R dot sine theta plus R times the derivative of sine theta with respect to time. So it will be cosine theta times theta dot is equal to 0 because the derivative of a constant is 0. Okay? Now from this equation it is easy to find what R dot, which is the derivative of R with respect to time, which is the speed. So it is equal to minus R theta dot cosine theta divided by sine theta. Okay? Of course, here we are assuming that sine theta is different than 0. Okay? So this ratio will be defined. Now, I can continue. So starting again from this equation, we can calculate the second derivative. So we have R double dot sine theta plus, you put R dot again here, then you differentiate it with respect to time. So we will have cosine theta times theta dot plus. Now here it is a little bit tricky. You have the product of three functions, okay? The product of three functions. And you are differentiating this product with respect to time. So let's take R cosine theta as one piece and theta dot as another piece. So what we will get, d R cosine theta over dt times theta dot plus, we put here theta dot, then we multiply theta double dot, then we multiply it by R cosine theta. Okay, of course this will be 0. We just put here the 0. Now let's take only this piece. So we have the derivative of R cosine theta with respect to time. So this gives me what? We have the product of two functions and we are differentiating them with respect to time. So what we get, you get R dot cosine theta plus R times the derivative of cosine theta with respect to time. So it will be minus sine theta times theta dot. Okay. So to summarize, R double dot sine theta plus R dot, let me just put here theta dot cosine theta plus R dot, so I'm going to put this here, cosine theta plus R, just put here minus R theta dot sine theta plus, it has to multiply it here, it has to be multiplied by what? Theta dot plus R theta double dot cosine theta is equal to 0. Okay, good. Now, at theta is equal to 60 degrees, we can evaluate r using this equation, okay? Using this equation. So r will be equal to 0.4 over sine 60 degrees. Okay, so it is 0.4 divided by sine 60 degrees is equal to square root of 3 over 2. So we can write it, 0.4 divided by sine 60 degrees. So this gives me 0.462 approximately meters. Okay, now the same thing for r dot. So r dot we calculated from this equation. Okay, we have r dot is equal to minus r theta dot cosine theta over sine theta, and this gives me minus r, which is 0.462 times theta dot, they give it to me 0.45 radians per second, times cosine 60 degrees divided by sine 60 degrees. So if you calculate this, we will find, let me just calculate for you. We have cosine 60 degrees 0.5 divided by sine of 60 degrees, which is pi over 3. So this gives me approximately 0.133 meter per second. Recall that r dot is derivative of r with respect to time, and this represents the speed, okay, the radial speed. Now the acceleration can be calculated from which equation? From this equation, okay? So you just take r double dot, okay, leave it on the left hand side of the equation and take everything to the right hand side of the equation, okay? So if you do the math, you will be able to calculate r double dot, okay, and you will find equal to, here is negative, we forgot here the negative, so we have to put here the negative, you will find equal to 0.1, approximately 192. Okay, so this has to be in meter per second square. Good? Good. Now I have r dot, I have r double dots, and I am given theta is equal to 60 degrees, theta dot is equal to 0.5 radians per second, 60 degrees is pi over 3 radians, and I have theta double dot is equal to 0 because, why? Since theta dot is constant. Now using this information and this information, we can calculate AR and A theta. Okay, so we know AR is R double dot minus R theta dot squared. So this gives me 0.192 minus R, which is 0.462 multiplied by 0.5 squared. Okay, so should be able to find 0.192 minus 0.462. I'm using my computer to calculate this, is equal to approximately 0.0765, okay, meter per second square. Then we can calculate also A theta, which is equal to, or transverse acceleration is R theta double dot plus 2 times R dot theta dot, and this, as we said just now, theta double dot is 0, so the whole thing goes to 0. Then I am left with 2 times Now let me just put 0 here, plus 2 times r dot is equal to minus 0.133 times theta dot, which is 0.5 minus 0.133, because 0.5 times 2 gives me 1, so minus 0.133 meter per second square. Okay. Now that I have the radial and transverse accelerations, I can go back here to this equation 1 and equation 2. So if I solve these two equations simultaneously, I can calculate both the normal force due to the action of the support, the horizontal support, and the other force that is exerted by the arm OA. Actually, this side, only this side of the arm, okay? Only the right side of the arm OA, which is the force F, okay? So let's just go back here and look at the equations. So we have equation 1. Okay, we have this equation. Let me just copy this equation here. And we also need to bring the other equation. Let me just write it. mg sine theta minus n sine theta. So we have mg sine theta minus n sine theta must be equal to MAR. Okay, must be equal to MAR. Okay, now solving these two equations, we should be able to calculate both N and F. N will be equal to approximately 19.4 newtons, and the force F approximately 0.356 newtons.